Hello everyone, I am Pragya Srivastava. I am here to record a lecture on VLSI technology. The course code is KEC053 and presently we are discussing its unit 4, that is diffusion and ion implantation. Previously in my lecture we have discussed the basics of diffusion. Now we are studying, in my today's lecture we will be studying diffusion in silicon and likewise diffusion in various different kinds of semiconductors. And another topic which will be covered in my next lectures would be ion implantation. The two of them are the method to create a new or a different type of semiconductor in the form of well in already existing different semiconductor. So diffusion is a process by which controlled amount of impurity is introduced into semiconductor. Previously I have told, let's say we have a p-type substrate. Then diffusion is a process in which we can make a n-type well in existing p-type substrate. So this is the required process to introduce selected amount of dopants only into the already grown crystal, be it bulk material or it can be a epitaxial material. So it describes the process by which atoms move in a crystal lattice. In silicon technology, diffusion allows formation of source drain, and we can source drain of metal oxide semiconductors. Devices, the active regions of bipolar transistors can also be made using diffusion. Here we have to study diffusion from a limited source or constant impurity source. In the practical system, diffusion of dopant follows the compensatory errors function doping profile, which is very much abrupt. Now the total impurities lies in the thin shield of the total impurities lies in the thin sheet of charge and which is very close to the surface of semiconductor. So when the source is shut off, there is no possibility of new impurities. So we can see when the isolation layer is on, that is called when the source is shut off, there is no possibility or any impurity coming into the semiconductor. So it is called constant total impurity case. So the total amount of impurity is fixed by the time of pre-deposition and the temperature of pre-deposition. So we can very well control the total amount of impurity, after which the impurity cannot be added, before which the impurity cannot be added. The amount of total impurity has gone into the surface, remains there and gets further driven inside the semiconductor material. So this step is also referred as drive-in step. It is drive-in step. Here we have seen that as the time advances, let's say it is the time like 0th second, it is the time at which we are having 2 nanosecond, 3 nanosecond, 4 nanosecond. So at the 0th second, the doping and the impurity is only at the boundary. So the thickness is of course very much less. As the time advances to 2 nanoseconds, the thickness has come on to, let's say this is 1 nanometer. Then the thickness has come to 2 nanometer. Then time is advancing and the thickness has come to 5 nanometer. And again the time is advancing and the thickness has come on to 7 nanometer. So this is limited source diffusion profiles. Here we have the we are studying the related bipolar transistor formation by successive diffusions. So here we can see that the first curve is showing n-type, the second curve is showing p-type Gaussian, and the third curve is again with this straight line is showing n-type background. So here is the impurity concentration, and for n-type we can see that it is starting and it is falling again, and of course it is only extending till the depth is reached till XEB. Okay, so now again the p-type doping, now when the n-type layer has stopped, we can see that this is n. So this is n. So when n-type growth has stopped, means XEB, that is XEB emitter base is equal to 1 micrometer. So when this 1 micrometer has come, so we have to stop n-type diffusion. After that, after this, like when we move ahead of 1 micrometer, we need p-type. So we start p-type diffusion and then we have to stop p-type diffusion when the boundary of base and collector is hit. So when the distance comes in between XBC and XEB, that is in between 1.4 to 1.0 micrometer, we have, for this difference, we have p-type diffusion. So this is p-type diffusion again. Now, after 1.4, after a distance of 1.4, we again have n-type doping. So here we are making N, P, N transistor, emitter, base and collector. So this is how bipolar transistors are formed by successive diffusions. Constant impurity source diffusion is ideally suited for those cases where a relatively low value of surface concentration is required in junction with high diffusion depth. So the base diffusion of a bipolar junction of a bipolar silicon transistor presents this type of situation. The doping profile of bipolar transistor formed by successive Gaussian and error function diffusion into silicon wafer with a collector background concentration is 3 × 10⁻16 atoms per cubic centimeter as shown in the previous figure. So here we can see the n-type impurity is added by assuming infinite source. P-type impurity is added assuming n-type constant source, and then high temperature is of course used to assess this process of diffusion profile. Next we are going to study arsenic diffusion in silicon. Here we see arsenic has low misfit factor and can be incorporated into high concentration without causing strain in lattice. So since it is not causing any strain in lattice, so it is having a higher misfit factor. So the materials and the semiconductors which are like easily accommodatable in the lattice, they are having high misfit, they are having low misfit factor. The concentration dependent diffusivity of arsenic in silicon is described by H times di naught plus di minus n by ni and divided by ni. So this complete term is nothing but the diffusivity. Here two terms in diffusion coefficients. Here there are two terms in diffusion coefficient. The first term is the independent of dopant concentration, and the second term is proportional to the dopant concentration. So when the first term, we talk about first term which is independent of dopant, the second term is dependent on dopant concentration, means the diffusivity when is independent of dopant concentration is a different term as compared to when the diffusivity depends on dopant concentration. That is determined by interaction of arsenic with singly negative charged vacancies. Here we can see the concentration of arsenic in silicon will be closer to the surface concentration over a large length of large depth, and then it will fall steeply at the junction. We can see that here we have the error function for arsenic here, and then we have error function of boron here. We can see fall in concentration in the junction is more steeper than complementary error function. So this is the error function and this is the error function of arsenic. So we see that how the error function is falling as compared to the correspondingly error function. How the what we can call it, fall in concentration for arsenic, this one, and the curve is this one. So fall in concentration for arsenic can be seen as compared to fall in concentration with error function. Boron and silicon. Similarly, we have boron is an accepted type of impurity. We can see here we had this, and there we are N by Ni, intrinsic, and I represents intrinsic. Here we can see accepted impurity, and hence we have this plus sign, P by Ni. That place we had N by Ni. Boron is an acceptor type impurity, so it will interact with the positively charged vacancies. So therefore the concentration dependent diffusivity of boron is given by d H times di naught plus di plus, this is the plus sign for acceptor type, P divided by Ni. In both cases, it results in steeper, more abrupt profile than predicted by the complementary error function for infinite source diffusion, obviously, because d is not really constant here, but there is the term which is proportional to n. So we can see this is the fall of concentration for boron, which is this one. So both are different from the error function. Error function is this part. This one is the standard error function. Phosphorus in silicon. The concentration dependent diffusivity of phosphorus in silicon is described as d is H times, we can see di naught, di minus, n divided by Ni plus di square, n square divided by Ni square. Near the surface where the dopant concentration is very high, of course at the surface is the place where the dopant concentration is initiating. Dopant concentration is starting from the surface itself. The concentration and the dopant and the impurity, whatever we call it, entering from the surface only. So the concentration is highest at the surface. Near the surface where the dopant concentration is very high, the dominating term is going to be d proportional to the Ni square. The surface concentration is almost constant and it falls abruptly as we move on by increasing the junction depth. As the dopant concentration starts to fall very steeply, the position of Fermi level changes. So this is a new point here. As the doping concentration changes, the Fermi level will move from close to the conduction band and to the mid gap point. We can see here is a diagram where we can see the total phosphorus concentration and the electron concentration, and then we have the charge ion and the pair dissociation region, and we can see this is a kink here, and of course have to start with a graph which shows us the behavior between the junction depth x and the concentration. We can see the concentration here. So excess vacancy concentration is defined by this curve, and emitter DIP effect, we can see we have to start from the very beginning. We can see that this is a region of high concentration. We can see, of course, the region of high concentration. Why? Because this is a place which is near to the junction and it is just at the surface. So at this point which we are very close to the boundary, the concentration is very much high, and we can see that the diffusivity is proportional to square times of n. N is concentration. So as we are increasing the junction depth, or as we are increasing the depth inside the semiconductor, this falls abruptly. We can see that this falls abruptly. In this diagram, we can see that this curve is different. It's falling. It's falling. This is called the tail region. One is high concentration region and the other is tail region. And here we can see that it is d is equal to some constant, and this is also, there is a region of high concentration, there is a region of tail region, and then there is a region of transition region. So we have to start like this. Further, initially we have a high concentration region, then we have a region of transition like this, and then we have a region of almost constant. I'll draw it like this. So this is constant. Of course it will end, and here also it will end, not like this, but it will be ending very smoothly. So high concentration region, and then transition region, and then the tail region. So this is the diffusion process by practical diffusion system, or we can say by oxide of dopant. So diffusion is, once again I'm going to tell you that it is a high temperature process. The temperature ranges from 800 to 1200 degrees Celsius, and it is carried out in fused quartz tube, inside a fused quartz tube which is using a furnace, and there is inside that fused quartz board silicon is kept. So silicon sample is placed inside the quartz board, and it is exposed to this high temperature in which the dopants are present. So we are having a quartz board, and in that quartz board we are of course providing high temperature, and we are of course introducing the dopant gases. So diffusion process proceeds by high temperature. Semiconductor with the impurity species in contact, it serves to drive in. Here we can see this is the drive-in method we have studied before. Drive in to impurity to the desired depth and the surface concentration. The end goal to achieve dopant uniformly across the surface area, and we call it solid source technique. We have a diagram related to this. This is that diagram. We can see, of course, this is a quartz board, and I am drawing the heaters. These heaters will very efficiently increase the temperature. So we have the heaters at the top and also at the bottom. So this is a quartz board, and we can see that this is a susceptor. On that susceptor, these are the wafers. On that susceptors, these are the wafers. So we have, we can see that here we have a carrier gas. So these carrier gases are allowed to enter inside with the help of some control mechanism using valves and the flow meter. So what we are having? We are having the semiconductor, we are having the wafer. On that wafer, we are allowing the gas. Also, there is a high temperature condition prevailing inside the quartz diffusion board. And we can see that these gases, when exposed to the wafer, they will diffuse and they will form and settle a layer. They will settle and form a layer on the wafer. So this is solid source diffusion system. Next will be liquid source. When here the entry will not be a gas, here it will be a beaker or a container where liquid will be present, and out of that liquid we will convert it into some state so that it travels and enters inside the boat. So this is next is liquid source diffusion, and we can see the platinum board is used here. The platinum board is used to hold the solid source of the dopant species upstream for the carrier with the semiconductor wafer. In operation, the gas carrier transport wafers from the source and deposits them on the semiconductor slices. So vapor, liquid, there is a liquid source of diffusion. The vapor pressure of sources is critical parameter, and we can see, as I have explained in the last slide, there is a liquid source which is a temperature control bath. So this is a bathing solution, bathing source. And next is the carrier gases. The gases are being allowed, and there is a valve present here, and of course there will be heater. The heaters are there to increase the temperature, and of course the diffusion will take place. Liquid source diffusion. So this was all about diffusion from my side. I will continue and start an implantation from the next slide, next lecture.